Set the clock and start them. All right, clock's ticking on you, Group 12.
All right. Good afternoon. Thank you for coming out to see our presentation. We are Group 12. I'm Maribel, this is Sebastian, and Ryan. And our project was an SME student competition to build a remote inspection device. Our problem was based on the tsunami and earthquake that hit Japan in March of 2011. The nuclear industry issued a request for proposal to build a proof of concept robot that would enter the facility, inspect for damages, determine radioactivity, and protect the operator from any exposure since you're using a robot. Some of the specifications for the competition that are required is to navigate around objects, locate the pressure gauge and report the reading, push a button to initiate the cooling pump, pick up and drop off a radiation sensor, and all of this has to be done within 5 minutes. And the operator is behind a wall, so they can't see the competition, the layout of the. And now I'm going to pass it on to Sebastian, who's going to talk about the design of the robot.
Thank you. So I'm going to talk about, we went through several different stages in our design. I'm going to talk about the main characteristics of each design, and some of the setbacks and what we did to improve on that certain design. So this is our first design, which you would be able to see in our poster. Originally it has the caterpillar tracks. This design proved to be very inefficient. It requires 4 motors, so it needs more energy. And we found out that it was going to be very smooth terrain. We didn't have to navigate over any kind of rough terrain, so there was no need to have that kind of system with the skid steering. So our second design was a pivot steering system. It's got 2 drive wheels and 2 caster wheels in the front, and the arm. In this design, the arm was not strong enough to hold the camera, which how we initially intended it to use. So for the third design, we incorporated a separate pan and tilt system for the camera, and so we had to modify the chassis for that. But the downside of this were the caster wheels. The caster wheels made the steering very unpredictable. Let's say you had just made a right-hand turn and you were to go straight. In the time that it took the caster wheels to settle, you would send your robot in a different direction. So there's always constantly having to make corrections on it. So this is our final design, which is what you see in front of you right now. We manufactured the chassis base out of a cutting board, and I'm going to go into a little bit of detail about each of the main components. So what we use for the steering is a ball caster, and the benefit to this is it has no input on the steering. The ball caster is big enough, it's a 1-inch ball, so it's big enough to navigate over any kind of irregularity in the surfaces. And this is the pan and tilt system that we used. As you can see here, it's just a motor it's a servo that's in the back of the GoPro case with the wire hanging onto the chassis, and every time the motor moves, it tilts the camera up and down. This servo on the bottom here serves as our pan, and this we had to make special spacers for it in order so that the camera was low enough so that when the arm reached over it, it wouldn't interfere with the arm, but it couldn't be too low where the case of the camera would interfere with the bottom plate. So this is the bottom of this is what the bottom of the robot looks like. As you can see here, you have the communication wire, the video wire. This is a switch regulator, and we had to put it at the bottom because it was causing noise. It was creating noise with some of the video system and the communication, so we try to isolate everything as much as possible. So a little bit of detail here. You got the motor controller here. This is what allows the drive motors to go forward and back. This switches the voltage, the polarity of the voltage with our input from the microcontroller. And this, you can kind of see an idea of how big the motors are. They're very small, which actually ended up being one of the downfalls of this project. But I'll go into that in a little bit. The communication, we decided to go radio frequency. We were originally going to use Wi-Fi, but in order to incorporate the global learning aspect of this project, we used radio frequency. And it actually ended up being very well in our favor. A lot of the teams that competed, their biggest downfall was Wi-Fi. There was a lack of it. So this helped. This alone was allowed us to place high in the competition. And then for the video receiver, as you see, what it used to be was a beer cooler, and we modified it. We gutted it all out and put all the components. You got the battery, you got the receiver, you got the switches, and this is the video transfer. So you know, very neat, very nice looking. There's a lot of nods. We've got a lot of nods at the competition for that one. Piggyback on the back of the robot is the switches. Each switch controls a different battery, and as required by SME, we need to have an emergency stop button. And now Ryan is going to speak about the robot arm in this construction.
All right, good afternoon. I'm here to discuss the principle that we applied for the robot arm project that we did. On the right side of the screen, you see this robot arm gripper that we attached to the robot arm. It consists of polycarbonate material right here, and we attach anti-slip material in order for it to grasp materials firmly. And on this side of the screen is the arm link legs. We built it like this with aluminum brackets and with polycarbonate materials as well. We attach some fasteners in order to secure firmly. The robot arm basically consists of 5 servo motors, excluded the base and the vehicle itself. Attached to it is a prefabricated claw, as you've seen in the previous screen, with a modified gripper on it. In order for us to make this possible, we have to use lighter materials such as aluminum and polycarbonate plastics. The rotating base that we attach to the robot arm in order for it to move 180 degrees. We use a kit available, and we have to assemble it and incorporate it to the robot arm in order for it to use it. All right, for the motor selection, we need to do this correctly, so we have to find out the amount of weight it has to carry, and because on the initial designs that we have the heavy components. We keep the heavy components such as motors as close to the robot arm base as possible. As Sebastian mentioned earlier in the initial designs that we have, the camera itself is attached to the robot arm, which is proving hard to be difficult for the robot arm to move because it's adding weight for the robot arm to be moved on it. So we have to change our design and attach the camera to the base of the vehicle with its own servo motor to have it pan and tilt down. All right, and I'm passing it to Maribel to discuss the program.
So this is a basic layout of our program. We used a switch function in order to have preset commands for each key input. Basically, to control the drive, to control the camera, to control each joint of the robot arm and the base and the claw. But the most interesting thing that we did with our program, which since the time was such a key component in our competition, what we did is we made preset positions, and this helped us save time during the competition. So we have one to pick up that would lower the arm close to the ground and open the claw. So then we just have to do minor adjustments to be able to pick it up. Then the travel position would retract the arm, but leave the sensor and the end of the claw in view of the camera, so that just in case it falls or anything happens, we can quickly see it because it's in view, and then just pick it up or anything. When it's ready to drop off, there's a drop off position that drops it low to the ground, and then you just press the open and it releases it. This is good so that we don't break any sensors in case it's very sensitive and so forth. And then the home position to just get it out of view, retract it completely, when we're not using it. And there's a few for the camera as well. A little bit about our finances. We had a budget of $1,000, but due to inexperience and replacement of parts, we exceeded this budget also with traveling all the way to Alabama. Was a lot more expensive than we had predicted. Now I'm going to pass it on to Sebastian with the competition.
Okay, so this is a video of our competition. You have on the left-hand side, you're going to see what the operator was seeing just at the beginning of the competition. So you started off with the sensor, and this view wasn't as clear on the control room, which the control room, it was totally isolated. The drivers before the competition even got set up, they were isolated. Cell phones were taken away. So the operator had no idea what the course looked like. Now, this was done on a basketball court, and these lines, it looks very easy and very clear right now, but through the video transmission, you get a little bit of fuzz. It was hard to see where the boundaries were. So right now, it's being put into, this position is the drop-off position, so as you can see, the claw came, brought it close enough. You want to make sure you don't want to just drop because if the sensor falls off, then you won't get points for it. So, by the way, this video is not real time. It's sped up about 2.5 times. So just picture everything going a little bit slower. This is the sensor that we had to pick up. This competition was said to have been one of the hardest ones. If you look at previous videos, if you look at videos online of other competitions in other districts, for example, the walls that other districts had, it was just like a little 2x4 or something. So a lot of teams, what they did is they actually created a camera that was higher up so they could see the overview of the whole competition. But this advantage was not possible here. There was, I didn't see any videos in the competition where they had water bottles or you'll see a towel put in there somewhere. So there's a lot of things that can snag up teams, and it caused a lot of issues. So right now the sensor got picked up, and now we have to go and read this gauge. And all we have to do is we just have to report that number to the judge that was in the room with you. They didn't tell you if it was right or wrong, so if you didn't have good camera feed, you wouldn't have been able to they wouldn't tell you if you got it right or wrong. And so as you can see, there's a towel I was talking about, and here you're going to see the button that we had to press. You just have to touch the button. So as long as you touch the button, they give you the okay, they beeped it, and you were good to go. But going back to some of the obstacles, the competition, so a lot of teams, they decided to use like a sweeper arm movement to pick things up, and a lot of these obstacles, a lot of the towels, or especially the water bottles next to that sensor, it was getting in people's way quite a bit. So it definitely made it for a tough competition. And here, the video, you're going to see I kind of go back and forth quite a bit. I was having some lag in the video, so I held the turn button for too long. And this is coming back to the starting position. Okay. And then, so there was 30 teams that competed in total. The average team, the average team member was 8. That's how many people a lot of people had. There's teams who, the University of North Carolina that was posted next to us, they had 18 people on their team and they couldn't finish the course. So it's a testament to what we did, and we did something right. So out of all the 30 teams, FIU came in 9th place. For being the smallest team there, we were very proud of that, very, very proud of what we did.
Who was number one?
University of Kentucky. They had full funding, and they had all the hard work given to them. University of Kentucky actually was like 1st, 3rd, and 4th. They did well. So here's the conclusions that we've come and how we could have improved our placement. Because we had a right setup, we had a good setup, but the drive motors, the speed of the drive motors really set us back quite a bit. We had to sacrifice some speed for torque because they were a little bit too small, but we had already designed it. It was last minute. We had to continue with the same motors, just higher torque. If we had the camera placed higher on the robot, we would have been able to see the boundaries a little bit better. It wouldn't have been so confusing as to what was a boundary and what was just the basketball court. A lighter robot arm, we would have been possibly able to mount the camera to the actual claw so that we would avoid all the motors in the front. The shielding of the wires for the communication would have been much helpful, so we wouldn't get so much static out of the video feed. That was quite a bit static, so it made it difficult to navigate it. And next time, we're not going to drive to Alabama. We will fly to Alabama. That was a long drive. So we put a lot of effort into this project, and we put a lot of work into it, but none of it would have been possible without Southern Gear. They were a great help backing this whole project up, and also, of course, Melissa, our advisor. She was there to answer all our emails late at night, and we would get very detailed responses from her, so she shared a lot of her knowledge with us, and definitely made this project smoother for us. And that's it.
Very good. So Southern Gear funded this 100%?
No, they